Hi everybody, welcome to the Relativity module. Let's go ahead and start with a meditation. Go ahead and just finding your body, a comfortable position, and just doing a quick scan of your body. Just noticing if you have any tightness in your shoulders or your back. You can actually just start with a little stretch in the beginning here, just maybe reaching your arms behind you, out the side, rolling out your wrists, rolling out your neck, maybe circling your back, chest forward and back, your whole torso just rotating around. Just finding some movement to bring some blood flow in your body in case you've been sitting for a while or just doing something repetitive. And then settling in. Letting your body come to a place of stillness. Taking a couple deep breaths. Filling up your lungs and torso. And letting it out with a sigh. One more big inhale. And big exhale. Just letting go. Whatever you're coming from. Just arriving here in this moment. In the peace of no expectations. Just listening. Just being. Just breathing. Letting that breath anchor you in this present moment. And trying to keep your thoughts right here. Not in the future, not in the past. Just right with this breath, this body, in this moment. Just using the exhale to release anything that might be coming up. Clearing out that nice, wide open, empty internal space. Preparing yourself to be ready with a beginner's mind to encounter new knowledge. Just a few more breaths here. And coming back, taking another nice stretch, rolling out the neck, rolling out the back, rolling out the wrists, shoulders, standing, stretching your legs if you need to, and getting ready to dive right in. Thanks for that. So we're moving through this material in a roughly chronological manner, so we can kind of get an idea of the historical arc of how these ideas came to be, and looking at the ideas that were coming before and how they disrupted those ideas. And so in the past couple lectures, we looked at Copernicus's heliocentrism, Galileo's relativity, which is just to say that the laws of motion are the same for all moving frames of reference. So even if you're on a train moving at a constant velocity, things are still going to move the same as if you were standing still on the surface of the planet, which is also moving at a constant velocity as we rotate it around. And so we know that those laws of motion translate between moving frames of reference. Newton's classical mechanics or Newtonian mechanics describe those laws of motion, specifically with regard to mathematics, how projectiles move, how masses interact via momentum. Basically, all the laws that describe the world as a predictable billiard ball universe. With Newton's laws, if we know where each particle is and where it's going, we can predict everything else that unfurls from there. And that was the precipice of science before modern physics came around. Some things that they still weren't exactly clear on was the nature of light. So Newton thought light was particulate or corpuscular. Thomas Young in 1803, the double slit experiment, showed that light is actually a wave. Sophie Germain wrote the wave equations for describing those two-dimensional wave interference patterns on the Chladni plates. Germain's work in elasticity theory did eventually help with some of the foundations for relativity as well. Maxwell's laws of electromagnetism. From those laws, it was realized that light is an electromagnetic wave. So it's a subset of radio waves and X-rays and gamma waves and UV rays. All of these things are electromagnetic waves, and light is just one small portion of that larger electromagnetic spectrum. In 1900, Max Planck quantized light so that the black body radiation model would not end in the ultraviolet catastrophe, but would match the experimental evidence that we see of radiating bodies radiating at a specific wavelength and the higher frequencies not just draining off all the energy. Because with the quantization of light, it would require so much energy for the higher frequencies to radiate off that energy. It's just not available, so that curve drops off at the high frequencies instead of going to infinity because of the quantization of energy. And then we had the annus mirabilis. Einstein, likely in collaboration with his wife, Maliva Merrick, published 4 papers. The first one using Planck's constant to describe the photoelectric effect, which had already been experimentally known for a long time, that just shining light on a material can release electrons from that material. But the curious thing about the photoelectric effect that people had not been able to describe was why it was the frequency of the light that determined whether the electrons were released and not the intensity of the light. And so Planck's constant brought in that needed key to understand why it's the frequency that releases those electrons. The second paper described Brownian motion by describing the molecular motion, and we're going to get into this in this lecture. We're going to talk more about Brownian motion. We're going to get into Lorentz equations and special relativity, and to that famous equation E equals mc squared. In this video, we're also going to cover Poincare and Minkowski space, or the block universe, light cones, and we're going to get into general relativity a bit. And then in our quantum mechanics module, we'll cover some of these further developments of quantum mechanics that happened later in the 20th century. But for now, let's dive on into Brownian motion. Motion is this phenomenon where like a particle of pollen dropped on the surface of a liquid takes this very irregular path as it kind of dances around the surface of the liquid. And that had not yet been able to be described as to why is this an irregular path. Einstein, and in collaboration with Merrick, were able to describe in that second 1905 paper that the underlying forces of molecular motion, so the particles, the molecules of water, as they dance around in the fluid of water, are continually bombarding this grain of pollen. And it's the sum of their bombardments from all different directions and velocities that are creating this random dance of the pollen across the surface of the water. So Brownian motion hints at something else, which we're going to get into when we look more at fractals, which is the notion of Brown noise. You can see in these graphs here on the right-hand side, there's a difference. The two graphs on the very bottom where it says brown noise, you can see that kind of mountainous waveform there. And then the little graph with the black triangle on it is showing the power spectrum. So this image up at the top, right next to the Brownian motion title, is showing the difference between the waveform and the power spectrum. And so these two are translated between by a mathematical transformation called the Fourier transform. And what it does, it takes this red waveform that you see here on the left, and it divides it into its sub-waveforms. And so just like when you hear a guitar chord played, you hear it as one sound, that's that red wave, but it's made up of the sounds of all six different notes from the 6 different strings, if it involves all the strings. So let's say it's a 3-note chord, because we see 3 waveforms here. And so what Fourier transform does, it pulls out those individual strings and says, oh, there's this note on this string, this note on this string, and this note on this string. And when you play them together, it sounds like this red waveform. When you pull them apart, it's this kind of purpley violet magenta gradation here of these background waveforms. And we represent that on the frequency spectrum, this blue graph right here, where you see the spikes on that graph. That's where those predominant waveforms are on that graph. It goes from the longest, slowest waveforms on the left to the shortest, fastest on the right. So for brown noise, down here at the bottom, you can see, well, let's go through the other ones so we get an idea here. White noise at the top, you can see is very random. It's practically impossible to predict the intensity of the next spike in that wave there. And when we look at it in the frequency spectrum, that graph with the black rectangle, we can see that all of the frequencies, so the y-axis along the bottom, again, is on the left is the long, slow frequencies, and on the right is the short, fast frequencies. And they're all in equal power, so they all show up equally. There's no dominant frequency. Whereas if we go down one set of graphs to the pink noise graph, or 1 over f, it says, so it's the power of the wave is inversely proportional to the frequency of the wave. So that's what 1 over f means, f being the frequency, and 1 divided by the frequency is just showing the inverse proportionality. So if we take that y horizontal axis again and say the x horizontal axis, sorry, and say there's the long, slow frequencies are on the left and the short, fast ones are on the right. So the long, slow frequencies have the greatest power. That's why the black triangle has the tall side over on the left. And as you move to shorter, faster frequencies, the power decreases. And so this is a signature of pink noise, such that we can kind of see overarching undulations in this waveform. It's not as flat as the white noise. And so there's a bit of patterning there in the long, slow frequencies that the faster frequencies dance within. And then this becomes even more obvious in the brown noise. So brown noise is also called red noise, which is where pink noise gets its name, as being in between the white noise signature and the red or brown noise. So brown noise is related to Brownian motion because there is more predictability even within the randomness of the walk. So Brownian motion you can also think of as a drunkard's walk. So you know, a drunk person, you know they're going to take one step and it could be in any direction. but you know pretty much how far they're going to go, and there's a limited number of directions they can choose from. You can also think about it as exploring a city where you're going to walk one block in a straight line, and then you're going to come to an intersection, and you could make any decision as to which way to go in that intersection, but then you're going to walk in one block for a straight line again. So there's this measure of predictability, one step or one block, and then there's a decision point where randomness can be introduced. Which direction are you going to go next? And so pink noise tends to be this Goldilocks balance that shows up frequently between predictability and surprise, and brown noise is just a little bit more predictability, even though it is apparently random. So I just wanted to touch on Brownian motion. The noise signature stuff is going to come up again when we talk about fractals, but I just wanted to put it there in its appropriate historical place. So Galilean relativity, we talked about a little bit already. I'm just going to review it real quick because it's going to help us understand special relativity a little bit better. And so, like I said before, Galilean relativity is just about the physical laws working equally well in a fixed frame of reference versus a moving frame of reference. And what we can see here is the Galilean transformation. The y-axis, everything stays the same. The z-axis, everything stays the same. The time axis, everything stays the same. So that's where you see y prime. That's that little single quote after the y is said as prime. It's just to differentiate between the two frames of reference. So y prime is the moving frame of reference. Y is the original frame of reference. So y prime and y, same. Z prime and z are the same, t prime and t are the same. Where the difference comes in is in the x direction, because that's the direction of the moving frame of reference. It's moving in the x direction. So that's where we're going to have this transformation to help equate the laws in these two frames of reference, to translate between the two frames of reference. And we translate between them by this minus vt term here. And so that's just subtracting the motion of the frame of reference. So v is the velocity and t is the time. You can see down at the bottom here, I've shown the units of these. Velocity is in meters per second, or distance per time. You can use any units. And time is in seconds. And so when you multiply those two together, the seconds on the bottom of the velocity and the seconds of the time cancel each other out, and you're left with meters. And so when we see the x prime, that little red x prime term up there equals x minus velocity times time minus vt, that's minus another measure of distance. And it's the distance that was covered in a specific amount of time because that frame of reference was moving at a certain velocity. This is what's going to translate between this moving frame of reference and the fixed frame of reference, because what's different is the moving frame of reference has covered a certain distance in a certain amount of time because it's moving at a certain velocity. And so it's that term, that difference, that translates between these two frames of reference. This brings us to Lorentz, the Lorentz transformations, which are at the foundation of special relativity. And so here we can see again, we've got t prime and t is the foundation of this equation. These are the two frames of reference that we're translating between. But here in Galilean relativity, t prime equaled t. So the times were equivalent. Here the times are different, and they're different by this factor, this denominator here on the right-hand side of the equation. The square root of 1 minus v squared over c squared. V squared is the velocity, and c squared is the speed of light. As the velocity changes, this factor that translates between these two frames of reference changes. And that's what you can see on this graph here. The vertical axis of the graph is telling you time dilation, and the horizontal axis of the graph is showing the velocity as a fraction of the speed of light. So over on the right-hand side, you have 1. That means the velocity is totally 100% of the speed of light. Versus halfway through the graph, you have a 0.5, and that's showing you that the velocity is half the speed of light at that 0.5 section. At low speeds, at 0, 0.1, 0.2, 0.3, 0.4, the graph is starting to go up a little bit, but it really doesn't take off until after 0.9. At 90% the speed of light is when that time dilation just has an exponential curve there, and it's going to infinity. What does it mean for time to dilate infinitely? When we look at these terms here, we can say, okay, well, if one of these frames of reference is the speed of light, if we're trying to translate between a photon and a still frame of reference, then that v term has to be c also. So that denominator is the square root of 1 minus c squared over c squared. So c squared over c squared is just going to be 1. And if you have 1 minus 1, then you have 0. The square root of 0 is 0. So now you're dividing the time of the first frame of reference by 0 in order to get the new frame of reference. And so if you remember, when you have a 0 on the bottom of a fraction, that means that fraction is undefined. It is kind of impossible to translate. What you'd have to do is multiply the 0 by the other side of the equation, which would make t prime 0, which means there's no time passing in that second frame of reference that's moving at the speed of light. And so this is one place that we can approximate that idea that light does not experience time. And in this same equation, we can also see, okay, well, if we're not moving at the speed of light, what is the factor of time dilation that's happening as v is becoming smaller? How much is time dilating? All right, so that is the Lorentz transform, one of the bases of special relativity. Now, in order to look at the Lorentz transform in another way, we're going to need this handy tool. These are light cones, and these come out of Minkowski spacetime, which was published shortly after Einstein-Merrick's paper on special relativity. And in Minkowski space, you end up with this four-dimensional spacetime, articulated a little bit more thoroughly than in the special relativity initial paper. So a light cone, you can see here where these two cones touch in the very middle of the axes is here and now. Okay, the vertical axis is moving from the past through the here and now and into the future, and that horizontal axis is space. And so you can just see these two graphs right here. One's just a little more three-dimensional than the other, so you can see that plane of space in the square across the middle there. So space doesn't just go in one direction. It's really not just two-dimensional either, but we are limited to paper representation here. And so what the light cone represents is all of the places that light could have come from in the past. In the green light cone, it says past light cone. And all of the places that light can go to in the future from this point here and now. And so the slope of that cone is the speed of light. It's a measure of meters per second, of distance per time. And since we have that distance there on the horizontal axis and time there on the vertical axis, that's what the slope is. 3 times 10 to the 6th meters per second is the speed of light. So that's the slope of that cone in either direction. And so light only moves along the surface of the cones. It doesn't move inside the cone or outside the cone because it only moves at that specific speed. If it were to go slower, which would be less meters per second, then it would be inside the cone. If it were to go faster, more meters per second, it would be outside the cone. And so we know, since the speed of light is the speed limit of the universe, then we know that any 2 points outside of the cone cannot be causally connected until some point in the future where their light cones can intersect. So everything outside of the cone can exist in space simultaneously, but cannot communicate until some future point when light from one point could reach the other, or sound from another point could reach another point. This highlights the fact that even though you might be sitting with somebody and talking to them, you are not perceiving that person in your same moment of time. You are perceiving them as they were a split second ago when the light bounced off their face or the sound left their vocal cords. It took time for those things to reach you. So what you perceive of them actually happened a split second ago. It becomes more obvious when we look out into the stars at night and into space and recognize that we are seeing those stars as they were in the past. The further we look out into space, the further into the past we're looking. It takes 8 minutes for light to get from the sun to the earth. So if you look at the sun, hopefully not for too long, you're seeing the sun as it was 8 minutes ago. So we all exist inside the cone. If you stand still, you start at the here and now, and you just progress up that vertical axis into the future. If you're moving, you angle away from that axis based on what your speed is. You'd be very close to the axis if you're moving slow, and if you're moving faster, then you're going to angle out a little further away from that axis until you approach the speed of light, which is on the edge of that cone. Now that we've had a little basis for what the light cone is, we can look at the Lorentz transformations on a light cone. First, take a look at the black and white image on the left. The red lines are those C boundaries of the cone. The C is the speed of light. Once again, the vertical axis is time, the horizontal axis is space, but you might notice that now we have that x prime and t prime in here too. And so that's to say, in that moving frame of reference, the x-axis is going to angle away from the original x-axis, and the time axis is also going to angle away from the original time axis. At the speed of light, both these axes would collapse into that C line right there, along what's called a light-like curve is the C, the boundary of that cone. The distance between any 2 points inside the cone is a time-like curve, and the distance between any 2 points outside the cone is a space-like curve. And it's space-like because you can't have something outside the cone transition to another point outside the cone. If they're in the same horizontal plane, they exist simultaneously. So me and my computer screen, we exist simultaneously, but we only interact with each other at some point in the future where our light cones interact, where the light from the computer screen hits the future me, because we both have to move through time in order to cover the space between us. So two things separated in space are outside the cone, have a space-like separation, and only do they interact as light or sound from either one travels through time and meets up with the other one in the same place at some point in the future. Okay, so now the Lorentz transformation is the transformation of these two axes, right? From the x to the x prime, from the t to the t prime. And you can see there's kind of this scissoring action happening. No longer are x prime and t prime perpendicular to one another. They're angles kind of closing it. And you can see here in the purple section that black line is the trajectory of object. So say that's you. Say that black line is how you're moving through space and time. You're not standing still because you're not going straight up the time axis. You're not moving at the speed of light, but you're getting kind of close to it. You're more than, maybe 50%, maybe 60% the speed of light. And so at that speed, your t prime, your time axis, and x prime, your space axis, are going to be angled away from those original axes that would be the perspective of somebody who is standing still. And so that orange rectangle is showing how you, that black arrow, would look from the perspective of somebody who's standing still. You would cover that much of the orange space and that much of the orange time. But from your perspective, you've got that purple T prime and X prime. And so that purple parallelogram inside the orange rectangle, you can see how it looks like your T prime, it looks like a shorter amount of time compared to the orange T, where the orange rectangle comes to. And you can see how the X prime portion of the purple parallelogram looks like a much shorter distance than the distance represented by the orange rectangle. And so it's this scissoring of the axes, the bending of space and time, that makes time from a moving frame of reference, moving close to the speed of light, act differently than it does when it's not moving. It's worth noting that Heinrich Lorentz and Henri Poincaré had been in dialogue pretty extensively around the Lorentz contractions and the development of a theory of relativity specifically, pretty much simultaneous to Einstein's development to his 1905 paper. Poincaré had actually published a paper covering very similar material just a few months before Einstein, and then a more in-depth one a few months after Einstein. And the notable thing about Einstein's paper is that he doesn't include any citations or references, even though his work is obviously utilizing Lorentz transformations and other conventions developed by Lorentz and Poincaré. Einstein continued to maintain that most of it had been his own development while acknowledging some of Lorentz's earlier work. And other sources have noted that Einstein and friends had read and discussed Poincaré's earlier work also. So they're definitely in the intellectual field. The one main thing that distinguished Einstein's theory from Lorentz and Poincaré's was that he did away with this notion of ether and did away with the notion of either of the reference frames being a primary or true reference frame. Most of the other developments in the theory had already been in circulation. He was able to simply bring it together in a new, more elegant way by disposing of these extra concepts that were kind of being residually held onto. Then, of course, Minkowski made it geometrically visualizable, as we see with these rotations around light cones in space-time, the rotations of these axes were a development by Minkowski. So here's a visualization of that scissoring of the axes and how it affects the order of events. So when these axes are perpendicular to one another, straight up and down and horizontal, wait till it comes back to it, that A, B, and C events, bing, all at the same time. But when they scissor like this, from the perspective of a moving frame of reference, that's what it's showing when they scissor, you can see that the order of these events shifts. Bing, same time, scissor, C, B, A. Scissor the other way, A, B, C. So there's this alternative ordering of events that happens with the scissoring. So from the different perspectives, events are going to happen at a different time because of the flexibility of space-time. Whitehead talked a lot about what Pythagoras would think if he could see all the different places his theorem and his work has gone from the cyclicity of the circle to the wave to some of the fundamentals of relativity. And so let's take a second just to review it real quick as we build into some of its uses in relativity. So the Pythagorean theorem is simply that a squared plus b squared equals c squared. And so it's really about that triangle in the middle of the image here. You can see the length of each of its sides are labeled a, b, and c, with c being the hypotenuse, that longest distance opposite from, this only applies to right triangles, so opposite that right angle there between a and b. So one way to visualize this, because it's squaring each of those lengths, you can make each of those lengths into the side of a much larger square. And so that c squared square that comes off to the upper right angles off to the right is a representation of the area that is c squared. And so when you square c, you're moving from a one-dimensional length to a two-dimensional area. And so the Pythagorean theorem, part of its brilliance is that it reveals that this relationship between one-dimensional lengths, the lengths of that sides of the triangle, is a relationship between two-dimensional areas. And so you can see here that it's a squared, which is that square with the a length sides, plus b squared, which is the square with the b length sides, plus c squared, which is the square with the c length sides. And that defines the relationship between a, b, and c. And so if you didn't know one of those, the lengths of one of the sides of the triangles, but you knew the two others, you could always find that third length by using this formula. Now, the Pythagorean theorem actually comes in this fundamental equation that Einstein is so famous for of E equals mc squared. Like Einstein's other accomplishments, of course, he did not come up with this in a vacuum. Mass energy equivalents had already been established for electromagnetic energies. Einstein's development was to extend this to all forms of energy and to show how it relates to relativity. So in this equation, E stands for energy, m stands for mass, c is the speed of light. And we can understand this equation a little bit better if we take a look at this triangle over here, which has E as the hypotenuse, the energy, and mass times the speed of light squared is that side over there on the right. And then on the bottom, we have P times C. And P is the momentum. The momentum is the mass times the velocity. P equals mv. The interesting thing about this equation is that if the object is at rest, the velocity equals 0, so the momentum equals 0, because that momentum equals mass times velocity. P equals mv. If v is 0, momentum 0. If momentum is 0, that whole green term vanishes. You can imagine that triangle just collapsing as the PC length gets smaller and smaller and smaller until the E, the energy, equals the same length as the mass times the speed of light squared. And so this is where E equals mc squared comes from. It's for objects at rest because they have no velocity. Likewise, the Einstein-Minkowski-Bloch universe uses a similar equation. Here, the triangles mean change in or an increment of. S is the proper time, and so that means the combination of space and time. And that equals the sum of x squared plus y squared plus z squared minus ct squared. And so, once again, trying to figure out a way to incorporate time into this very spatial equation, right? So the Pythagorean theorem was a squared plus b squared equals c squared. Now we have an increment on the x-axis squared. plus an increment on the y-axis squared, plus an increment on the z-axis squared, minus an increment on the time axis squared, because we have to somehow differentiate time from the spatial dimensions of x, y, and z. And together, those give us an increment of proper time squared of the combination of space-time. The proper time, S, is the time that a clock at a specific frame of reference will read. Relativity tells us that time goes slower when things go faster. So if you put a clock on an airplane, fly it around the world, and then land it back down again, that clock will show an earlier time than a clock that was left on the ground because it was moving at a very fast velocity through space, and therefore was not moving as quickly through time. So that's what this proper time shows us, that S variable, proper time, the combination of an object's movement through space and time, is showing us what the clock will read based on the movement of its frame of reference. The T measure of time, however, shows how a clock would run by the distant observer, not affected by the velocity of the frame of reference. So T is the clock that got left on the ground in the airplane example. It's showing how that still clock would run. But why is time multiplied by c, by the speed of light? This was a convention that Einstein-Merrick introduced, and then Minkowski took it and put it in this Pythagorean form, where time is subtracted instead of added. Notably, the conventions of sign can be reversed also. Space could be considered negative, and time could be considered positive. The main idea is just that they're opposite signs, space and time, so that there's a finite amount of space-time which must be distributed between them somehow. But let's look back at this question as to why is time multiplied by c? So once again, if you look at the dimensions used, so the speed of light is a speed, it's a velocity, and so it's in meters per second, or distance per time. And when you multiply a velocity times time, you are multiplying meters per second times seconds. And when you've got seconds on the bottoms and being multiplied by seconds, you can cancel those seconds out and you're left with meters. And so time is spatialized by multiplying it by the speed of light. And I say it's spatialized because it's turned into units of distance instead of units of time. And so this was the convention that Einstein introduced, was spatializing time. Then Minkowski came and made it geometrical and made it visualizable through light cones and through those scissoring of the axes that we've seen. So here, where time is spatialized, it's introduced as a negative, as an opposite sign to the space. And so it's detracting from the spatial movement. And so there's a sense in which there's an allotment of space-time that objects can move through, and they can use it by moving through time or by moving through space. If they're not moving through space, if they're at rest, then they're moving through time at a certain rate. Whereas if they're moving through space at a certain velocity, they move through less time. So for light that is moving at c, at the speed limit of the universe, the proper time, that s value, is 0. So its movement through space and its movement through time cancel each other out so that it doesn't move through either from its own perspective. These paths of light are called null geodesics, and so they're showing the shortest distance between 2 points in space-time. These are also the paths that light cones travel. So Minkowski space was defining this notion of s squared as the proper time of that combination of the movement through time and space. So here on this light cone, we can see that when s squared equals 0 is the path of light, that slope C edge of the cone, that particular relationship between space and time, where space and time cancel each other out. And these points, the A, B, and C points here, are just to show the time-like separation and the space-like separation, with A and B being a space-like separation, so they're existing at the same point in time, but cannot interact until some future point in time when their light cones intersect. And A and C are a time-like separation, so A and C could be the same object, just at different times, C being in the future of A. Now, the interesting thing about this proper time equation of Minkowski-Einstein space-time is that in this equation, when time squared is negative, how do you take the square root of that negative number to get time back out of it? What happens is that you end up with imaginary time. And so let's look at imaginary numbers for a second and see why that might be helpful. So this is the circle of I, or what's called the Wick rotation. Let me just orient you real quick before we get into how it's all related. So the origin point is just where the horizontal and the vertical axes meet there in the middle, the 0 point. And if you follow the horizontal line across to the right, you see there's the 1. Across to the left, it goes to -1. If you look at the vertical axis, it goes up to I and down to -I. So if you'll recall, I is equal to the square root of -1. It's an imaginary number because the square root is actually translating between dimensionality, right? So if I square a number, it's taking a linear quantity and making it into a two-dimensional surface. If I take 2 times 2, I end up with a box of 4. If I take 3 times 3, those are just the lengths of the sides of the box, and I end up with the area of the box. The 9 is 3 squared. 4 squared, 16. So to take the square root of a number is to go backwards in that dimensionality, from a two-dimensional surface to the length of one of its sides, of the length of the side of a square specifically. So to take the square root of a negative number, so to go backwards in dimensionality from something that was already an absence rather than a presence, starts to get a little bit beyond the bounds of what our minds can conceive. So it really has no physical reality. That's why it's called an imaginary number. Yet these prove to be very useful in many mathematical domains, including relativity, quantum mechanics, any form of trigonometry, the study of waves. Over and over and over again, I shows up again, yet it has no physical counterpart. Nobody really knows what it means, yet it holds an essential component in generating mathematics that produce real-world results. So that's what's fascinating about the mystery of the circle of I, of imaginary numbers, and Wick rotation. And so one thing imaginary numbers does is it gives us an additional axis to work with. So normally we think of, we have, the width of something as one dimension, we have the height of something as another dimension, and we have the depth of something as another dimension. So we have 3 dimensions to work with of regular numbers. But if you think about imaginary numbers as giving us another dimension to work with, so just as the imaginary axis is perpendicular to the regular horizontal axis, just as any other dimensions are perpendicular to one another, so that the imaginary axis gives us the 4th dimension to work with. So as you can see here, we've got that imaginary axis, and this is called the complex plane. So any number that involves imaginary numbers is called a complex number. So why imaginary numbers are so helpful in dealing with anything that cycles, like waves, is because when you multiply anything times an imaginary number, it has very interesting results, right? Because if I is the square root of -1, then we know that I times I, same thing as I squared, is going to equal -1. So let's just work with that as we go through the circle here. So if we start at the top of the circle at I, and we multiply I times I, then that rotates us around. You can follow that arrow on the circle down to the -1. I times I is -1, as it says in that quadrant. Then if we multiply that -1 times I, then we get -I. It takes us down to the bottom. If we multiply -I times I, we get 1 instead of -1. That takes us up to the 1, and then we multiply the 1 times the I, and we get back up to the 1 at the top. And so it's this built-in cyclicity, cycling, into the mathematics of the equation, which works beautifully with anything that likes to move in circles. As many of you might observe, there are numbers of things that like to move in circles in nature. So the unique dimensionality of I, giving us another axis to work with, a fourth dimension, it allows us to solve problems that are unsolvable in a previous dimension. This is often how mathematicians, if they hit up a problem they can't solve, if they add another dimension, they're able to find a solution. Lewis Carroll, who was the pen name of mathematician Charles Dodgson, you might recall Lewis Carroll was the one who wrote Alice in Wonderland. He was in fact a conservative mathematician, mocking imaginary numbers through the childlike story of Alice in Wonderland. There was actually quite a bit of mathematical commentary that went on in that story, but the Mad Hatter's Tea Party specifically, an endless rotation around the table because time had left them stuck at 6 o'clock, was specifically a stab at the non-physicality, the meaninglessness of imaginary numbers. And it ties into time specifically because imaginary numbers are used in general relativity to describe the timelessness of a block universe, to give us a fourth dimension of time, to imagine a universe with time able to be present, like laid out on a timeline as a fourth dimension with the rest of the spatial dimensions. Another fascinating place that imaginary numbers show up is in an imaginary dialogue, a soft consciousness dialogue, an active imagination that physicist Wolfgang Pauli recorded in his dialogues with Jung and Marie-Louise von Franz. And these are his words. He is speaking with a woman, the piano teacher. And he's saying, the I makes the void and the unit into a couple. At the same time, it is the operation of rotating a quarter of the whole ring. And she says, it makes the instinctive or impulsive, the intellectual or rational, the spiritual or supernatural of which you spoke, into the unified or monadic whole that the numbers without the I cannot represent. To which he says, the ring with the I is the unity beyond particle and wave, and at the same time the operation that generates either of these. She says it is the atom, the indivisible. When I spoke these words, she gave me a significant look, but it seemed to me not necessary to say Cicero's word for the atom aloud. And as a side note, I think when I looked that up, like what would have Cicero's word for the atom been? It had to do with the body. It was kind of a diminutive, a sweet term for the body, the physicality. And then Pauli's dialogue continues, and he says, it turns time into a static image. She replies, it is the marriage, and at the same time the realm of the middle, which you can never reach alone, but only in pairs. Though not specified by, here we go, Cicero's word for atom is corpusculum, It's a diminutive term for the body, implying a double entendre, as it also used an affectionate reference to the female body. So this active imagination was written by Wolfgang Pauli in 1953 in a kind of meditative state. It came to him, but it really speaks to the unique position of the complex plane for bridging the magical, the mathematical and the philosophical, the subjective feeling realm of relationships and the seemingly abstract, dry, objective realm of mathematics. As another fun aside, while we're talking about Wolfgang Pauli and Carl Jung, one of the subjects that they frequently discussed and refined together was the notion of synchronicity. And one profound synchronicity that showed up for Pauli was that when he was in the hospital dying of pancreatic cancer in 1958, he was 58 years old, born right at the turn of the century when all of this was coming in, one of the founders of quantum mechanics. He noted to his assistant, "Oh, do you see the number of the room?" And the room number he was in was 137. And much of his life he'd been preoccupied with the fine structure constant, which is 1 over 137. It relates the strength of the electromagnetic charge between two charged particles. And it's one of those fundamental constants it's like, why would it be that number? 137 is also significant because it's a phi ratio of the degrees in the circle. It's a phiath of 360 degrees is 137.5 degrees. Anyhow, so a synchronistic occurrence, a little nod there to him in his final days from the unus mundus, the one world that he and Jung would refer to, that gets revealed and hinted to by these synchronicities. The imaginary formulation actually originated with Poincaré, and he used it to show the Lorentz transformations as a rotation of Euclidean spacetime. He used a notion of imaginary time to show that. So the idea that in this second equation, time is not only multiplied by c, but multiplied by I, its imaginary number, such that when you square it, you end up subtracting that t times c, because I squared is -1. It makes that last term negative. And so this idea of a rotation in space-time coming or relating to the rotation, Wick rotation, of that imaginary axis that provides an alternative dimension for this fourth dimension to differentiate itself from the spatial dimensions, in the sense that it has this directionality of the Wick rotation built in. Since I squared equals -1, since by definition I, or any imaginary number, is the square root of -1, so when you square I, you get -1, then the negative temporal term becomes positive when time is imaginary. As you can see, as we move from that top equation where time squared is negative to the second equation where time becomes imaginary, but then when we square it, it becomes positive. And so here the imaginary number provides a function of an alternative dimension, of a fourth dimension, like the complex plane gives you that vertical axis of imaginary numbers. The imaginary numbers provide a fourth axis to the three spatial dimensions, allowing for a four-dimensional space-time to be mathematically articulated without space and time having to be specifically detracting from one another, but in a more triangular relationship, specifically like the Pythagorean theorem. So Minkowski's geometrical formulation of special relativity allowed Einstein and possibly Merrick, they were still together by the time general relativity came out in 1915, but their relationship was more strained, so it's harder to say what level of collaboration Merrick may have had in the development of general relativity. But the geometrical formulation of special relativity by Minkowski allowed for the development of general relativity, which instead of just allowing space-time to be flexible and to change, it allows space-time to curve. And so not only is it stretchy and can dilate and contract, but it can now curve also. And we see evidence of this in how light travels around gravitational objects. So the picture here on the top, you can see those kind of arcs around these two stars, and those arcs are the light from galaxies behind these stars being smeared out and stretched as they follow the path of curved space-time around those stars to our eyes. So you can see a couple different diagrams of what's going on there. Here in this bottom left, if you imagine you're standing there on Earth and the sun or a star, any massive gravitational body is there in the middle, and there's another star behind it, which we would normally think we wouldn't be able to see anything directly behind a massive gravitational object. But because space-time bends around that gravitational object, light will take the path around it rather than down into its gravitational well, because that would be the longer path in space-time, and light always takes the shortest path between 2 points in space-time. So it goes around massive gravitational objects, but also gets smeared out in the process. Here's another illustration of that same gravitational lensing process, where you see the actual position of the star directly behind this gravitational well created by a star or a black hole or something. And while we wouldn't expect to be able to see a star directly behind another star, the apparent position of the star can be smeared out onto both sides of that gravitational well as it bends around, and we see that light coming towards us from the side of the gravitational well. We assume that the position of that background star follows a straight line of our line of sight, and so it appears to be on the side of the gravitational well instead of behind it. Light cones can also help us visualize this bending of paths of light, because it involves light cones tipping over. As light travels around a massive gravitational object, its light cone tilts, which means space and time. So time being that vertical axis that goes straight through the cone turns. As time bends, the light cone changes its orientation, which brings about the fun speculative possibility of closed time-like loops, such that that vertical axis of time going through a light cone, if it can bend, what would keep it from bending back on itself, such that it's moving forward in time, yet it shows up in the past cone of that original light cone. It went out through the future and showed up in the past. And so this is the notion of a closed time-like loop. One place we might imagine this happening is in the belly of a black hole, where space-time curves so dramatically that it pinches off, that space and time actually change orientations for one another, such that a light cone going into a black hole, there's a flop of space and time within it, and theoretically it could come out backwards in time. And so people are often looking for, well, where are the white holes? Where are the symmetrical versions of the white holes where light is being released? And perhaps a white hole is simply a black hole backwards in time. Those particles that are falling in, if you look at it symmetrical in time, are actually all coming out. So backwards time could look no different than forwards time because our perspective is simply one perspective in time. We might be coexisting. I like to talk about this as Merlin time. Merlin in the King Arthur stories lived backwards, but nobody experienced him as acting any differently. But his experience, if you try to imagine what his experience would be like as to living backwards, it can be quite a brain twister. But this backwards time could simultaneously coexist with forwards time and really be fairly undetectable. And so this might be a possibility for the emergence of things like non-locality and the violation of locality and of a finite notion of finite space-time and things being separated by space and time. If particles can move backwards in time, then we could be receiving information from the future in subtle ways that maybe we're just not that skilled at picking up on yet. Just like humans had to learn to remember, perhaps we need to learn to cultivate our powers of receiving information from the future as well. Pure speculation, but fun to play with. So here's just different ways of conceiving of particles moving in different directions in time, with space is our vertical axis and time is our horizontal axis, and a black hole here on the left, everything's falling into it. No white hole backwards in time, where everything's coming out of it. And if you just remove those arrows of direction, they look pretty much the same. And this is riffing on a notion of particle-antiparticle creation and annihilation. And so normally it's thought of this diagram here on the left, where once again space is our vertical axis and time is our horizontal axis, and those arrows are both going forward in time. So P on the bottom is a particle, P with a line over it is its antiparticle. The idea is that in empty space, the quantum foam, particles and their antiparticle pairs are continually emerging separate and then colliding again and annihilating each other. So being created and annihilated, created and annihilated, created and annihilated, and that's the quantum foam. Somehow our universe is mostly particles and not antiparticles, so somehow those got separated in the creation of our universe so that we are not continually annihilating. That separation allows there to be something rather than nothing. The alternative conception here, as developed by John Wheeler and Richard Feynman, is this diagram on the right where the particle is moving forwards in time, but the antiparticle is moving backwards in time, just that little arrow switch right there. And so these two nodal points on the end are the point of creation on the left and the point of annihilation on the right. But simply with a switch of perspective, you can have the particle moving forwards in time to the point of annihilation, which is really just a turnaround point for it to become an antiparticle moving backwards in time to its original creation turnaround point and become a particle moving forwards in time. John Wheeler also speculated that there could only be one electron by recognizing the ability to move forwards and backwards in time and by enlisting the powers of the positron, its antiparticle, to move backwards in time. Laurent Notal further developed this idea that the uncertainties in energy and the divergence of scale and therefore particle path length that emerge on very small scales could be dealt with by understanding diverse particles as manifestations of the same particle. Imagining one particle is bouncing both backwards and forwards in time, creation turning around into its antiparticle and then moving forward in time, just following this arrow track here, starting at the bottom left, and you've got a particle moving forward in time, and then from a normal temporal perspective, it finds an antiparticle to collide with and disappears. But from a reverse time antiparticle perspective, it just turns into an antiparticle and moves backwards in time for a little bit until it turns into a forwards in time particle again, backwards in time antiparticle, forwards in time particle, and on this zigzaggy path. And these dotted vertical lines are counting up how many particles there appear to be in between those lines at that point of time. So in the first section, we're just seeing one particle. In the second section, we're seeing two particles moving forwards in time and one antiparticle potentially moving backwards in time. In the next section, we've got three particles and two antiparticles. And then the same for the next section, and then back down to one particle in the final section. So perhaps this is just one particle bouncing back and forth in time instead of particle-antiparticle pairs creating and annihilating one another. This is another way to interpret Hawking radiation as well, where if we look at the A point here, Hawking radiation is the discovery that black holes do actually radiate particles. Black holes do have hair, as it said. They don't just suck everything in. There are things that can escape, and they escape by this particle-antiparticle pair creation happening right on the event horizon, such that the antiparticle, in this case, gets sucked in to the black hole, and the particle is released. In a sense, that means that the antiparticle came out of the black hole and became a particle. You can see in this second diagram there, with the antiparticle going backwards in time to come out of the black hole, switches direction after the event horizon and moves on forward in time. So you can see how things quickly can change the perspective just by allowing for this introduction of a backwards in time motion. Einstein's equations of general relativity have a number of different solutions to them. One of them was the solution for a black hole, which then was initially a theoretical prediction before it was observed as an astronomical reality. Another prediction that Kurt Gödel proposed for Einstein's birthday is known as Gödel's universe. And so it is a legitimate mathematical solution to Einstein's equations. And what's unique about it is that it contains these closed time-like curves that we looked at when the light cone bends and bends and bends so that it returns to its own past. And so this outermost circle on that plane, you can see says it's a closed time-like curve. And if you can look at those little light cones right there, they're laying on their sides and circling around this closed time-like curve. Whereas the center circle there says a closed null curve, and the null curves are the path of light. And so the light cones there are showing that this circle lies on that slope of the light cone. It's tracing out the edge of the light cone. It's the path of light right here. And within the path of light is a closed space-like curve, which might be something more like the spherical Earth, such that when you move in one direction, you come back around you can walk all the way back around to where you started, just by moving in the same direction the whole time. And so this is just a fun alternative conception of what might be possible somewhere in the universe. There might be these closed time-like curves, and it's just a matter of perhaps finding them and learning how to interact with them. Okay, we're going to leave it there for now, having come through quite a journey from Brownian motion to special relativity's Lorentz transformations and Minkowski's formulation of the block universe, that four-dimensional space-time defined by proper time using imaginary numbers and the possibility of backwards moving particles. And so I hope you enjoyed this little journey and our readings and other videos for this week, and look forward to the discussions. Thanks for listening.